Did you able to see my slides? We will wait for 5 minutes, then we will start. Hello, good afternoon. Did you able to see my slides? Someone please respond. Hello, good afternoon. Did all of you able to see my slides? Hello. Hello, good afternoon. All of you able to see my slides? Hello, someone please respond. Then I will start. Hello, hello. I am audible. Hello. Please someone respond. I am audible or not.
Yes, sir, you're audible.
Okay. Thank you. My slides are visible. Yes.
Yes, sir.
Okay. So we'll
Yes,
start.
sir, it's visible.
Okay. Okay. We'll start now. So before starts, so let me introduce about myself. 1 minute. Someone have microphone on.
Sir, yeah.
Hello. Hello, Robini. Please mute yourself. Thank you. So now I will start. So before that, I will introduce about myself. So I am PMRF students pursuing my PhD at IJM Mohali. So the course name is the Introduction of Polymer Science and course instructor as Professor Divakar Dhada. So this one as 8 week course. So we are already 1 week online session I have already done. So today the next session. So we will solve some mathematical question and some problem which are during this week what set taught. So first I will tell about that what is the functionality. So when we do the polymerization, so when you do, so there will be, I'll tell earlier about that, there will be generally three type of polymerization. One is the addition polymerization, one is condensation polymerization, and another is the leaving type of polymerization. So so between this addition polymerization, which are the free radically involved, condensation, which are that condensate product involved, or the functional group are involved, and leaving polymerization will be different type like ATRP polymerization or ring opening polymerization. So when we are talking about the condensation polymerization, so condensation polymerization always involves some functional group. Like if you want to synthesize an ester, so there will be two functional group is needed, that is acid and alcohol. So if you want to synthesize a amide type of bond, so you have needed two functional group like amine and um, your acid group, like they are making the peptide bond, or you can call that CONH amide bond. So any condensation polymerization reaction are involved that two functional group, but when you are talking about the addition polymerization, there will be no functional group are involvement. So when the two functional group are involvement, then how can we calculate that average functionality of this molecule? Because when we calculate that that monomer molecular weight, so to calculate this monomer repeating unit molecular weight, so like in a polymerizations where there will be two groups are involved like R C double bond O, so like it will be ester like, and there will be some R1, which will be one side will be OH, and this side R side will be C double OH. So when there will be two functional group involved and we are talking the repeating unit molecular weight, so our repeating unit will be up to this. So when we're talking about the repeating unit molecular weight, so when we calculate this, so we have to know about that functionality. If you know the functionality, if there two groups are involved, like one acid, one alcohol, so the functionality will be of this molecule will be 2. So we have to divide it, this repeating unit divided by 2, which will be that original repeating unit mass. So to calculate this original repeating unit mass, already we solved some problem regarding this. So we have to know that about the functionality. So what is the average functionality, how we can calculate? So if a monomer A which have the functionality Fa, that means in this monomer how much that functional group are present, and monomer B, if that functionality is Fb, then that average functionality will be Fa, that is that functionality of this molecule into that number of moles, and plus Fb into that second molecule number of functionality are present into that moles divided by overall moles. Like an example, ethylene glycol, which has that two OH group are present in ethylene glycol, you know. So two OH group are present in the ethylene glycol, so that total number of functional group is 2, that is the functionality is 2. And glycerol, which have the three functional group are involved, so there will be total functionality will be 3. So one case is that is that ethylene glycol, another is that glycerol, which have the three OH group are present, so that is the total functionality is 3. Then that average functionality, what will be the average functionality? Average functionality will be that 2 into multiply, if they are taking like 1:1 molar ratio, so 2 into 1 plus 3 into 1 divided by total number of moles. If they are taking as 1, then the total number of moles is 2. So that average functionality of this polymer will be 2.5. It will be not 3 or not 2. So regarding this type of question, so we have to first question we have to solve this, that uh, the functionality of the citric acid in the polymerization reaction and ethylene diamine. So you have that. So any condensation polymerization, we need the two functional group. So any condensation polymerization, we need the two functional group. Uh, one is that acid and this are amine. So what type of bond they are making? So they are mainly making acid and amine. We are already told they are making amide bond. So they are making mainly amide type of bond. So if you know the structure of citric acid, so you know that citric acid is present in lemon. So and the structure of citric acid will be like this. There will be three COOH group present into your molecule, and ethylene diamine, which have that structure will be like this. The ethylene and two sides will be amine. So ethylene and amine. . So we have to calculate the functionality of this molecule. So what will be the functionality of this molecule? So this amine, where it will be react in alcohol or in acid? Someone, that this amine will react with this alcohol group? I am audible?
Acid group.
Yes. So this amine will be react only this acid group. So and how many acid group are present in this citric acid? So there will be three acid group are present. So our functionality should be 3. When that normal question asks about that where the polymerization can be start from this side, from this acid and amine can start the polymerization, this acid amine can start the polymerization, this acid amine can start the polymerization, but which group are not involved in the polymerization? So the functionality of this molecule should be 3. So next similar type of question, consider this following molecule, then we have to calculate the functionality of this monomer. So first in that reaction the product will be amide bond. So to form that amide links, so which are responsible to make that amide bond? This acid group, this OH group. So first we have to find out that how many functionality are present. So there will be one double bond is present, one C double OH, and one type of alcohol. So three type of functional group are present here mainly. So to making this amide bond, which will be involved, this acid group will be involved. So to making this, so functionality during to form the amide bond, so what will be the functionality? Someone, please. Did you understand? So making amide bond, so there will be two group are involved. One is that amine group and another is that acid group. So without acid and amine, there no possibility to make this amide bond. So only that amide will be formed when there will be acid or when there will be amine. So here no amine is present, only acid is present, and number of acid group is present is only 1. So that functionality to make that amide bond should be 1. Then the next question is, in that reaction that produces ester links. So making ester, which group are involved? One is that alcohol group and another is your acid group. So making ester, to make this making the ester, so where the ester can be grow. So from this side OH some acid can act react here and that ester will be formed. Here also one acid can act and here also one alcohol can attack react and that ester can be formed. So to making that ester link, so how many functional group are present in that in your monomer molecule? So three functional group are present. So the functionality of to making this ester bond will be 3. So amide will be 1, your ester will be 3. Then in the free radical ionic conditions, the reaction through the C double bond C. So when the double bond are involved in a reaction, so how many um, functionality can be produced? So the two side from the two side that molecule can grow. So for this reason, when there will be any double bond involved, so that functionality are doubled. So there will be total number of 3 double bond are involved here. So the functionality will be double. So it will be 3 into 2. So that amide link will be 1, ester will be 3, and that double bond will be 6. So that our right answer should be C, where that first will be 1 and that second functionality will be 3 and third will be 6 functionality. Then which of the following monomers are most suitable for the cationic polymerization? So you know the cationic polymerization. So any cationic polymerization, so there will be some involvement of carbocation. So we have to find out that between this monomer which have that more possibility to make this carbocation stable. So if you go the structure, the first one, the methyl methacrylate, the monomer structure will be like this. So if the carbocation is formed, so carbocation will be formed like this here. So if this carbocation form like this is your minus R, this carbonyl group. So it will be take out your electron from this carbon center, which will be, so if there will be some group like this, if there will be some group which can give that electron here, so that then the carbocation will be stable. If take out that electron from here, because the carbocation where at where at that loss of electron, so when there will be loss of electron, so you need to stabilize this carbocation by give some electron cloud to there. So if you want to take out from electron cloud from there, so it will be not at all stabilized. So we have to find out that, we have to know about that monomer structure. Then we have to find out that that monomer structure can stabilize this carbocation or not. So next one is that vinyl chloride. So the carbocation will be from here, and but the chloride have this minus I effect. One minute. Hello, আমি করে ক্লাস আছে আমার, রাখো। কি ঠিক আছে, রাখি দিও এখন। হ্যাঁ রাখো। So 1 minute. I'm audible, right?
Yes, sir, audible.
Yeah. So when there will be vinyl chloride, so vinyl chloride, there will be chloride group are present, and we want to make this carbocation stable. So it will be not stabilize your carbocation. It will be that, you know, any that halogen group which have that minus I effect. So this minus I effect cannot stabilize this, because this minus I effect means, so they will take out electron from this carbon center. So it will not at all stabilize this. Then your vinyl acetate one. So when the vinyl acetate can stabilize your this carbocation, so maybe this oxygen have that lone pair. So maybe this oxygen lone pair can stabilize this carbocation, but this oxygen lone pair more goes to this side, because there will be one carbonyl side. It can be go to that uh, resonant resonance structure. So this oxygen have probability go to two sides, like this carbonyl side, and can also stabilize this carbocation also, but not effectively stabilize this carbocation. So you need someone which have the more effectively stabilize this carbocation, like this vinyl methyl ether. So in compared to vinyl acetate, the methyl vinyl ether, which have that lone pair, can stabilize this carbocation. But vinyl acetate can also be stabilized, but not that much, because this oxygen lone pair can also go to that resonating site with this carbonyl group. So methyl vinyl ether can produce your carbocation. And next is that N-vinyl pyridine. So N-vinyl pyridine, the carbocation is from here. So this that some benzene group are present into that carbocation, so it will be go to the by the resonance to stabilize this carbocation. So among these, so there will be that first four which are not at all stabilize your carbocation up to vinyl acetate, but methyl vinyl ether and 4 vinyl pyridine which will be stabilize your carbocation. And when that polymerization take place, if that will be stabilize your carbocation, so that will be more favorable to from that cationic polymerization. So what should be your right answer? So right answer should be methyl vinyl ether and 4-vinyl pyridine. Okay, how this carbocation polymerization can take place? Like any carbocation initiator will be attack your methyl vinyl ether, and that will produce carbocation here. So if this carbocation, like this oxygen can stabilize this carbocation, like here it will be stabilize this carbocation, then it will be more favorable. But if you not stabilize this carbocation, so during polymerization, so first the carbocation is formed by attacking your initiator. Then if this carbocation are stable, then polymerization goes to the forward direction. If they are not stable, the forward direction are not possible. So to make the stabilize that carbocation, we need some group which will have that plus R effect or plus I effect, or some benzene group or some aromatic group in present beside that carbocation, so that will stabilize your carbocation and which will be suitable for carbocation polymerization. So our right answer will be methyl vinyl ether and 4-vinyl pyridine. So you know about that. So did you understand up to this?
Yes, sir.
Yes, sir. Thank you. So now we are going to that some condensation polymerization. So condensation, this guy are Walsh Carothers. So which will be not invent the Carothers equation. He is working on that DuPont industry, which are mainly making synthesize the polymer, and DuPont is the first which are making that nylon 66 polymer. So nylon 66 polymer, there will be involvement of adipic acid and hexamethyl diamine. So this guy also work in this DuPont, and from working there, so he will be establish some equation where we can calculate the degree of polymerization from the condensation polymerization. So like any condensation polymerization, so we involve some functional group like that. If the number of, so total number of molecules which will be react n0, if the initial number of molecule will be react, and n will be total molecules after given reaction period. So total amount of reacted. So earlier we are taking the total number of molecules is n0, and in between n0, so number of n will be reacted. So first, like if we are taking 10 number of molecules, and in between 10 there will be 2 number of molecules already reacted. So it will be like this, that total number of molecule we are taking 10, and total molecules after given reaction period, if there will be 2, so total number of so total product will be formed like 2, then how many number of molecules are reacted? So there will be 10 minus 2, like 8 molecules are will be reacted. So and that extent of reaction, what will be the extent of reaction? Like that extent of reaction will be total number of molecules you are taken, and that number of molecules which are reacted. So number of molecules reacted, it will be n0 minus n, and total number of molecules you are taken is n0. So from here we can know about that how much extent of reaction, so which will be given by this p. So from this I needed some mathematical calculation, for this reason I have taken. So you can calculate that extent of reaction by this Carothers equation, and from this extent of reaction we can also calculate the degree of polymerization, because the degree of polymerization is nothing but the ratio between that n0 by n, that is that total number of molecules taken and number of molecules reacted. So the degree of polymerization, if you put this equation is here, so it will become degree of polymerization like xn x bar will be 1 by 1 minus p. So n divided by n0, it will be become 1 by 1 minus p. From here also we can calculate that weight weight average degree of polymerization. So weight average degree of polymerization will be 1 plus p divided by 1 minus p. We can also calculate that number average molecular weight, which will be m0 into 1 by 1 minus p, where that m0 will be repeating unit molecular weight, We can also calculate that MW bar, like that, that weight average molecular weight, which will be M0 into 1 plus P divided by 1 minus P. Also we can calculate the PDI, because if you know that MW bar and Mn bar, so we can know about that PDI, and PDI will be 1 plus P. So if you just knowing about that extent of reaction, we don't know that you during the reaction what we are known, that how many number of moles we are given and how much extent of reaction will be happen, like 50% or 80%. So by only this calculation we can calculate the degree of polymerization, weight average molecular weight, number of molecular weight. So what needing in the polymer, that how many molecules are reacted during the polymerization, that all information can we know by this simple equation, by Carothers equation. So we can know about that PDI, we can know about that molecular weight, also we can know about that degree of polymerization. So then the first question was that the weight average molecular weight of an equivalent mixture of adipic acid and hexamethyldiamine. So this hexamethyldiamine and adipic acid are giving that synthesis of nylon 6. So diamine, which found out that molecular weight is 22,600, we have to find out that conversion of reaction. So if you find out that conversion of a reaction, so what do you want to find out? This conversion of reaction 1 by 1 minus P. And from here, what do we know about that? We know that molecular weight. So you know the molecular weight of this molecule. So molecular weight of this molecule is 20, this one 22,600, and also we know that M0 value. How can we know that M0 value? So M0 value we know, the molecular weight also know, we can calculate the degree of polymerization, right? So degree of polymerization will be total molecular weight divided by repeating unit molecular weight. So repeating molecular weight will be M0. So how we can calculate that repeating unit molecular weight? So we have to calculate that that numbers. So if you calculate, so what will be the repeating unit molecular weight here? The number of CH2 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 into 14, right? 14 means every group have that CH2. So it will be coming around 140, and the nitrogen and hydrogen will be 15 and 15. So it will be 30, and 1, 2, 3, 4, 5, 6. And there will be 2 carbon and 2 oxygen. So 2 carbon is 24 and 2 oxygen is 32. So total number of total mass will be, if you add this, so it will be coming around 6, 3, 2, 5, 3, 8. It will be coming 226. Is this 226 is the repeating unit molecular weight? Yes or no? Someone please response.
Yes, sir.
No, like I am talking about that when you calculate that repeating unit molecular weight, so and when there will be two functional group are involved, then what should I do? So you have to divide it this by
Divided by 2.
divided by 2. So that repeating unit molecular weight should be 113. So now you know that dp. So that dp will be, you know that 226. So it will be coming around 226 double zero divided by 113. So it will be coming how much? 200, right? So now you know that 200 degree of polymerization, and from Carothers equation what we know, that degree of polymerization equal to 1 by 1 minus p. So you know 200, so 200 will be equal to 1 by 1 minus p. So from here we calculate that p value. So now it will be easy to calculate the p value. So it will be like this: 200 minus 200p equal to 1. Now so from here we can calculate that p. So p will be equal to 1 minus 200 divided by minus 200. We can calculate the p from here. So it will be 199 divided by 200. So now we calculate the degree of polymerization, but here what tell that we have to calculate that weight average degree of polymerization. So we can calculate the degree of polymerization. Now if you calculate that xw, that like this equation I have already told, xw bar, it will be 1 plus p by 1 minus p. So xw bar already 200 we know. So now we have to put 1 plus p by 1 minus p. And we can calculate that p value. So if you calculate this one, so it will be coming around 99%. Then we have to calculate the feed ratio of adipic acid and ethylene glycol that should be employed to obtain the polyester. And number average molecular weight are given 86,000 and conversion is 99% conversion. So to calculate this, so first we have to calculate that repeating unit molecular weight similar way, like this, have the total number of atoms we can add, so that it will be coming around 172. So you have to divide it by 2. So you calculate that m0 value. So when we calculate that m0 value, so from here we can calculate that xn. Xn is the degree of polymerization. So we can calculate the degree of polymerization, and from there we can calculate also that extent of reaction already given, which is the 99%. So now we have to calculate that how this feed ratio we can take, so that that equation between relation between the degree xn, the degree of polymerization, and that reactivity ratio and extent of reaction will be 1 plus r divided by 1 plus r minus 2rp. So from here we can put this, all of this value. P value already you know, xn bar xn value already you know. So if you put all this value, we can calculate this reactivity ratio. What this reactivity ratio is told? So reactivity ratio is told that ratio between this adipic acid and that two monomer ratio, like ratio between adipic acid, if that it will be Ra and ethylene glycol, Rb. How much ratio we can take to get this molecular weight, which that extent of reaction is 8,600. So only we have to know this that equation, what that relation between that degree of polymerization and extent of reaction and reactivity ratio. If you know this equation, we can calculate that xn bar from that molecular weight value we know that extent of reaction P, so just we have to put into this equation and we can calculate that reactivity ratio. Did you understand? So similar type of question, what fraction of reaction mixture still exists as a dimer? So this will be given by simple this equation. So now so this will be nx, that number of moles, and and this will be n, and the relation between this extent of reaction will be, this x will be number of, so the mole fraction will be divided by number of moles between that the two um, two monomer, so it will be xn, and which will be relation by n by 2 divided by total number of moles, and extent of reaction already we know that 0.99, so and that x value will be 2, so we can put in this equation, we can calculate easily that mole fraction of this equation. So from this equation what we can calculate, like that we can calculate that reactivity ratio by only know that uh, the extent of reaction and molecular weight. We can also calculate that the reaction mixture still exists as a dimer. We can calculate that mole fraction. Also we can calculate the what fraction of reaction mixture is still in the monomer, so that will be given by this equation, Wx equal to x into 1 minus p square into p into x to the power minus 1. So you know that p value, extent of reaction value, and x r is 2, so we can calculate. So earlier cases, the total number of moles is in reaction, so total number of moles is 2 if 1 mole are taken. Now when we are talking about that weight fraction, so that the weight fraction always that will be 1. So for this reason it will be 1 minus 1, so it will be become to the power 1 minus 1, it will be become 1, so it will be 1 into 1 minus 0.99 square, and that still the reaction mixture still monomer Wx will be equal to 0.0001. So by only knowing this equation we can calculate, because we know that the extent of reaction and the x value, which is that weight fraction value, and earlier this x was that mole fraction value, not weight fraction, mole value. Now the next question is, in an externally added acid catalyzed polyesterification reaction of an equimolar mixture of diol and diacid, the time that was needed to reach that 98% conversion is 98 minutes, and calculate the time that get required that conversion 99% conversion. So first we have to know that what that relation between that kinetics and with that extent of reactions kinet, and so that for this equation, that relation between that time and degree of polymerization. So xn is the degree of polymerization and p is your extent of reaction. So relation between x and degree of polymerization and this kinetics ones, 1 plus C0 into Kt. C0 had the concentration of your acid, catalyzed one. So now we have know that T98% already given 98 minutes. So for so to get that time at 99.5%, so we have to know about that what is the value of C0 into K, the kinetics, the concentration into that kinetics value. If you know this concentration kinetics value, we can put into this equation and we can calculate. So to get this concentration and kinetics value, so we have to put this one, because that earlier 98 conversion we already know that 98 minutes. So the reaction will be complete at 98 minutes. So from here we can calculate that C0 into K value. So then we have to put this into this equation. So 1 by 1 minus P minus 1 divided by C0 K value already we know, and extent of reaction is given now, it's 99.5, so it will be 0.995, and if you put this into this equation, so it will become 398 minutes. So sorry, it will be 0.5 here. So C0 into K value is 0.5. So if you divided 199 divided by 0.5, so it will become 398. So just to convert, so already we are talking about that condensation polymerization. So to convert 98% to 99.5%, we need that much of time. So like only 1% conversion you need up to 300 minutes. So like I have already told that condensation polymerization, so the conversion and the molecular weight increase in the later stage will be very rapidly, but before that, that conversion and molecular weight will be go very slow. Like in condensation polymerization, the plot of that conversion and molecular weight will be rapid up to that 98% or up to 99%. After that, their molecular weight will be going, and this to taking the conversion to 98% and 99%, it will be taking more time. Then another question was the amount of benzoic acid should be added, 2 mole of adipic acid and 1 mole of hexamethyl diamine, to get that molecular weight value 12,000 and that conversion is 99.5. So here the benzoic acid is added as a impurity, like monofunctional impurity we are adding into that condensation polymerization. So how much monofunctional impurity we can add to get that molecular weight value 12,000 and conversion is 99%. So you know already that equation, the degree of polymerization. So from here you can calculate, and also we know that that relation between this R reactivity ratio and that monofunctional impurity one. So here that NB, so NB is your benzoic acid. So this NB for that benzoic acid and this NaAA. So why the benzoic acid is monofunctional impurity? Here that only that one end are functionalized and another end is blocked. So when it will be react at last, so that polymerization are not take place further. So when there will be two acid, two amine are involved, so it will be polymerization take place. But when the monofunctional impurity coming at the end group, then this side that no polymerization are taking place. So for this reason, so we are adding this monofunctional impurity to control that polymer that molecular weight of this condensation polymerization. So and the relation between this reactivity ratio and this monofunctional impurity will be in that ratio between number of moles of this. So if you added that acid as a monofunctional impurity, so that above one will be that your amine one, and that below one will be your total number of acid are involved into this reaction. So here the benzoic acid and adipic acid are involved. So total moles of this acid and above will be there your amine moles. So from here we can easily calculate. So from here that we can calculate that xn bar value. So that it will be 106. Because first we have to calculate that m0 value. So m0 between this hexamethylene diamine and adipic acid is already we have calculated 113. So you know that molecular weight. So you can calculate that xn bar value. And relation between the xn and this reactivity ratio will be xn equal to 1 plus r divided by 1 plus r minus 2 rp. So from here we can calculate that r value, that reactivity ratio, and from that reactivity ratio if we want to calculate that how much monofunctional impurity needs, so that equation between this reactivity ratio and monofunctional impurity will be that Na divided by NBB into 2 into NBF. So this says that benzoic acid monofunctional impurity. So you can calculate this one. So you need 0.51 moles to get that molecular weight 12,000 and 99.5% conversion. Did you understand this? So here only you know the equation between this degree of polymerization between that reactivity ratio, what that the relation between this, and also you know about that what is the relation between this reactivity ratio and this moles of that your two monomer and monofunctional impurity. If you know these two equations, so you can only you have to put into the equation and we can calculate easily that moles of monofunctional impurity. So these 3-4 equation we have to must know. One is that relation between the degree of polymerization and the reactivity ratio. One is that reactivity ratio with that monofunctional impurity, and earlier we are talking about this from the Carothers equation, that relation between that extent of reaction and between this PDI molecular weight and number average molecular weight and XW bar, all of this. So if you know these 3-4 equation, you can solve all of this problem. And also to calculate that mole fraction and weight fraction, to know these two equations. Now the next question is, which of the following molecules give the hyperbranched and cross-linked polyester when condensate with the adipic acid? So adipic acid already we know that that which have the two functional group are involved. So when we have that two functional group and we have that monomer which also have that two functional group, like if the adipic acid which have that two functional two acid functional group, and like your adipic acid which have CH2 OH. The structure of adipic acid will be like this. So when you have some molecules which have that two functional group, another monomer which have the two functional group, so they generally give that linear polymer. So if you want to get that hyper branched or cross-linked polymer. So if so you need that one functional group extra. So if your adipic acid involved in this reaction, so then that next functional group should be more than 2. So if there that another monomer which is the functional group is 2, then it will be not from that hyperbond, it will be that linear polymer. If they are more than 2, then that will be from that um, hyperbond or cross-linked polymer. So the first one is that ethylene glycol and ethylene diamine. So ethylene diamine, which is the that two functional group, ethylene glycol also two functional group, so it will be not from that hyperbond. Next is ethylene diamine and glycerol. Glycerol can form because that glycerol has that three functional group which can form this hyperbond, but ethylene diamine cannot form. Then glycerol and pentaerythritol. So this pentaerythritol have that more than two OH group. So this glycerol also can form the hyperbond. This pentaerythritol can also form that hyperbond. Ethylene glycol cannot form hyperbond. If you know the structure of pentaerythritol, so the structure of pentaerythritol will be like this. There will be four OH group are present. So to make this that hyperbond polymer, so you need that functionality more than 2. So if the functionality is 2, so we are generally getting that linear polymer. If they are more than 2, so we are getting that hyperbond or cross-linked polymer. Now consider the mixture, the following monomers along with their amount. So we have the glycerol 5 moles and succinic anhydride 5 moles. Then we have to calculate that average functionality of this molecule. So what will be the average functionality of this molecule? Someone. So this the general equation of what I have already told. So the average functionality will be functionality presence in that Na. So this will be the equation.
5.
So Fa into Na plus how much? It will be Fb into Nb divided by total number of moles. Na plus Nb. So first cases, the glycerol, how many functional group are present? So 3 functional group. So the functionality of
3.
this molecule is 3. So first one will be 3 into how much number of moles is 5. So 3 into 5 plus your next one will be number of functional group involved. There will be 2 functional groups. So succinic anhydride means that 2 acid group which are condensed here. So that 2 functional group. So 2 into 5. Now that total number of moles. So it will be 5 plus 5 because that glycerol also 5 moles and that succinic anhydride also 5 moles. So it will be 5. So above one will be 15 plus 10. It will be 25 divided by 10. So your average functionality will be 0.5.
2.5.
Right? Yeah. So there will be also one relation we have to know about that average functionality and that extent of reaction. So the extent of reactions of gelation occurs above this mixture. So there will be relation between that extent of reaction and that critical extent of reactions. After that, we cannot control the polymerization. So in that condensation polymerization, there will be some critical point. So after that, the molecular weight of this polymer are not controllable. So up to that, this given as that that notation like PC. with the critical extent of reactions. So for the relation between the critical extent of reaction and average functionality, PC equal to 2 divided by F average. So F average already we know it is 2.5 from this from for this glycerol and suctioning anhydride. So we can put directly here 2.5, so that 0.8. So it will suggest that after 80% conversion, so your polymers are not controllable. Up to 80% you can control this polymerization, but after that you have that above this critical extent point, so you cannot get uh, go to that polymer with the uncontrollable polymer. So up to 80% you can control this polymerization. So also this equation also you need to know that the relation between that critical extent of reaction and F average. So that next question was the polymerization between the equimolar amounts of adipic acid and ethylene diamine processed with the equilibrium constant 289. That K value are given and initial monomer concentration is 2 molar. The reaction carried out closed system without removal of the byproduct. So first we have to calculate that extent expected degree of polymerization. So that relation between this equilibrium constant and degree of polymerization will be xn equal to 1 plus k to the power half. So k value already given 289. So we can put this here. So it will become 1 plus 289 to the power half. So it will become xn will equal to 18. So the degree of polymerization will be 18. Now you have to calculate that extent of polymerization of this equation. So that extent of polymerization and that kinetics value which are related by this equation. The extent of polymerization PE equal to k to the power half divided by 1 plus k to the power half. So the k value already given 289. So you can put here. So you can calculate that extent of polymerization. So these 3, 5, 6 equation we must know. Like earlier by this Carothers equation, the relation between the extent of reaction and degree of polymerization, molecular weight, all of this. Then the next one will be that relation between that reactivity ratio and with that extent of reaction, reactivity ratio with that degree of polymerization, like this 5 6 equation. If you know, we can solve any problem. So up to this you understand maybe. So these are the last week class problem, that molecular weight. Did you calculate this molecular weight? If not, this will be the
9,940
so first you have to calculate number average molecular weight. So to calculate that number average molecular weight, so you know that Mn xi into Mi value. So you can do this. Mn is coming around 13,700. How to calculate 9,000? So you have to you want to calculate that Mn, you can calculate by Ni Mi divided by Ni also. Yes, we can calculate by this. Also, we can calculate by this equation also, xi into Mi. And to calculate that MW bar, so yeah, that NIMI square divided by NIMI, you can put it here. So it will coming around 18,133. And this the PDI will be MW divided by Mn. it will be 1.32. So how we calculate 9,000? It will be wrong here or something. So you
Sir, I
multiply.
considered 3000 instead of 40 for 0.15. So it is a mistake.
Okay,
I'll correct it, sir.
okay, yeah. So here will be the solution. You can take and recalculate it. Okay.
Sure, sir.
So then next question also that you have to know that relation between the weight fraction and molecular weight. Then we can calculate this equation. So that Mn, yeah, already I have given that equation. The molecular weight, the weight with that weight fraction Wi into Mi. So if you note that already the weight fraction and molecular weight, we can calculate that Mw, and to calculate that Mn, so the equation between this weight fraction and molecular weight, it will be 1 divided by Wi divided Mi. So Mi already know, weight fraction already know, we have to divide it, you get that summation value, and from there we can calculate that xw. So xw is that the degree of polymerization related to that weight average molecular weight. Also we can calculate that number average degree of polymerization. So to calculate that xw, we need that mw, weight average molecular weight, not that number average molecular weight. So to get that degree of polymerization, you need that xn, that that mn by m0. So your xn will be mn by m0. But when someone talking about that xw, that is that degree of polymerization due to that weight average molecular weight, then that will be xw, which will be mw by m0. This also last class question, so you can see that solution in match with your. So up to this, you understand. So here I am generally mainly I am focusing that problem and I am solving that problem. If you know like also I can discuss some topic, then I solve some problem. If that will be better, or just I will solve the problem, that will be better. Hello. Which will mm, someone please. Yes. So which will be helpful for you if I uh, talking some that if you want to solve some problem, if you go some basic around this question, that will be better. Like I'm telling some that related some topic, then I will solve this problem, that will be better, or I can directly solve some problem, so that will be better.
No, sir, better just tell the concept, basics, then to solve the problem, sir. It will be helpful.
Okay. So from next class onwards, I will do like that. I will do that basic one first, then I will solve the problem. Okay.
Okay.
So so today's class you understand that. So today's class mainly that if you know that equation, you can solve this problem. Yeah. So to like maybe I will tell that how this equation coming in the next classes. So generally you have to remember this that equation, that what are the relation between the degree of polymerizations with that molecular weight, all of this. So if you know this, you can calculate easily. So how this Carothers equation come, and this that relation between the reactivity ratio with that molecular weight or that degree of polymerization. So I will this topic I will do the next classes. Okay.
Okay, sir.
So today's is up to this. If someone have any doubt, we can tell regarding today's problem session. Do you have any problem? If not, then we will stop here. We'll meet in next classes.
Okay, sir. Thank you.